Welcome to the second of these lectures, two lectures on Hermann Minkowski and his contributions to 20th century mathematical physics. The first lecture was on Minkowski's, in some sense, obvious contribution to relativity theory. He provided Minkowski Space-Time, which is the space-time in which Einstein's relativity theory fits. Now, you may say, well, what did Minkowski actually add by adding Minkowski space-time to the theory? And the answer is that in some ways Einstein's is a very peculiar way of putting the relativity theory, because for the most part what you want from a theory is not what it makes relative, but what it makes invariant. Theories are characterized by their invariance properties, and the relativity theory has as its invariant essentially the light cone. So Einstein emphasized the relativity of time, that is, what your clock is going to measure is dependent upon your frame of reference and how fast you are moving in that frame of reference. And so it's, in a sense, it's emphasizing a point which is not directly able to characterize the theory. What Minkowski did was put into the theory Minkowski space-time, but what that does is make it clear that the invariant of the theory is the invariance of the speed of light, which means the invariance of the light cone, or also called the null cone, because the null cone is the same in every reference frame. And the null cone has very peculiar properties because any interval along it is zero in the Minkowski metric. So the null cone is the important object. This, in a sense, was emphasized by Minkowski, who made exactly the point that I've just made, that relativity is really not the point. What you want is Minkowski space-time because it is the invariant structure which he called the world postulate. The world, meaning, in a sense, the invariant in the world, that absolute world postulate is contained in Minkowski space-time. Now, this was not something that the physicists were, at the time, were emphasizing, were interested in. The physicists were interested in the fact, which was a revolutionary fact, that time was relative. This was something which had not really occurred to anyone. And it was, of course, Einstein's great contribution to have emphasized it, to make the point and to emphasize it. For the mathematical point of view, however, it's not the main thing. The main thing is the invariant, and the invariant is the speed of light, and that means the null cone structure of Minkowski space-time is the real thing that we're interested in. Okay, that's what Minkowski had formulated in 1908, barely 2.5 years after Einstein had given his relativity theory in 1905. And the consequences of all of this were not really properly understood, perhaps, until really the 1950s to 60s, because then there was the next big step from Minkowski space-time was taken by a Russian mathematician by the name of Alexander Danilovich Alexandrov, often abbreviated to AD, A.D. Alexandrov. And he noticed that, in fact, you only need one postulate to give you the entirety of the relativity theory in Einstein. Einstein, recall, had made two postulates, the basis of his relativity theory. In what Alexandrov did was notice that you could do everything with one postulate. And it's the one postulate that, in a sense, was there in Minkowski himself. He could have done this himself had he lived, I think. And that was the invariance of the light cone gives you everything. You don't need anything else. The invariance of the light cone is all that you need in relativity theory. So this was noticed by others later, and it was noticed then in 1965, somewhere around there, maybe a little bit later, up into the early 70s, it was noticed by Roger Penrose, who I mentioned in the last video. Now that was set the theory on the road to being better understood. The whole idea of Minkowski space-time had, in a sense, lain as an object that was not really correctly understood from the time of Minkowski, really through to the 60s. But in the 60s, there was a great deal of work based on Alexandrov's work, I might say, not with Alexandrov not being acknowledged in this, but okay. So there we have it, and we have this, and this passes into Penrose's work in the 60s and in the 70s, and therefore onwards into the view that we have it today. Okay. Now that's relativity theory in Minkowski, his important contribution. This difference in emphasis between Einstein's presentation of the theory as a relativity theory and Minkowski's presentation of the theory as a theory of the absolute world, this had, because Minkowski's contribution wasn't properly understood, this had a profound effect on 20th century philosophy, oddly enough. And that is that many people from that point onwards began to say, increasingly in the 1960s, that everything was relative. That was the claim. In particular, the claim was that all truth is relative. This was an truly astonishingly popular thing to say for a long time. And it was certainly resisted very much by philosophers, although there were some that joined in on this. But it was really a profound mistake. And you can see that how problematic it was, because this generalization from relativity theory, which made perfect sense, makes no sense when you generalize it to the claim that all truth is relative. For the very simple reason that there's nothing then for it to be relative to. There is something in relativity theory, in Einstein's relativity theory, for things to be relative to. It makes sense for velocities to be relative. It makes sense for distances to be relative. You can work that out because you have this absolute structure, which is the light cone structure. But if you say all truth is relative, that makes no sense, because what is it supposed to be relative to? There can be no answer to that question, because whatever it's relative to is then going to be something absolute. So all truth is relative is a nonsensical claim. And it's an unfortunate thing that it gained traction from this completely false relationship or equivalence with relativity theory. Now, the second thing I want to talk about, second contribution that Minkowski made that is worth understanding, is the subject of convex sets. This is a subject that Minkowski added greatly to in the years before he got involved with the discussions about relativity theory, which really only occupied the last 2.5 years of his life. But before that, he had been investigating the subject of convex sets. Now, I'll give a simple idea of what a convex set is by showing you examples and giving you a sort of an understanding of them. Convex sets come in two kinds. One kind is called a convex body, and much of what Minkowski was interested in was convex bodies. So a convex body is something like, let's say, a triangle, an equilateral triangle, or an ordinary triangle, any triangle. A circle, a sphere, that is the outer shell of a ball, is a convex set, a convex body. Let's see. The 5 Platonic solids, cube, octahedron, tetrahedron, icosahedron, and dodecahedron. These are, if you were to think of them as external parts, just the shell, as it were. These are convex bodies. What is not a convex body? Well, a crescent moon is not a convex body. That crescent shape is not convex. A cup is not a convex body. What about a cone? Well, a cone in some ways is regarded as a convex set, but it's not a body, as it were. But it is a convex set. And it's worth remembering that Minkowski was interested in convex sets in relativity theory because the light cones, the 2 light cones, at every point in space, these are convex sets. Well, how can we characterize convex sets? Well, they are the same, if you're sitting inside one, every point in that set is visible to you. Nothing is hidden, as it were, around a corner. Take a non-convex set. Take a Z, and think of it as sort of a hollow shape. So it's a Z like that. Now, that's an extreme example of a non-convex set, because almost any point you occupy in it, you can't see every point in that Z. There are things hidden around the corners from you. So it's non-convex, but any concave shape is not going to be a convex set. So this subject was being investigated by Minkowski, and he used what he understood about convex bodies in his description in relativity theory. So how then do we understand the relevance of these convex sets to quantum mechanics? Well, one way of understanding them, as it were, stepping back from quantum mechanics, is to think of a color space. If you were to take the primary colors as constituting the edge of that convex shape of colors, and you mix the colors, then what you will get is a color that is, as it were, inside a mixture of the primary colors. By primary colors, I mean, white, black, red, green, orange, blue, etc. Red, green, yellow, blue. These colors can be mixed together in proportions. So 40% red, 60% blue. So as we mix the colors together, we get something which is internal in that space. So the pure states of around the edge, as it were, the hull of the convex body is given by the pure states at the edge. So the mixed colors, the colors that are arrived at by mixing, are given as internal points, as points within the hull of the shell of the pure colors, the pure states. So That is how we arrive at them. Now, here's an important point to note about this, about the color example, because it's significant for later. There are many colors that can be arrived at through different mixes of the pure colors at the outside, as it were, at the rim. And our human perceptual system can't tell the difference between these identical mixed colors and between one another within that mixture. So the mixtures can be indiscernible to the human perceptual system. There are many different ways of getting exactly the same shade of brown by mixing different colors to get the brown that's, as it were, formed from them. Okay, so that's the story of convex bodies and the general notion of a convex set. What Minkowski showed was what I just said, namely that the convex body, the hull, is given entirely by the set of the pure points, the pure sets, if you like. Now that is significant because of the way that these convex sets, convex bodies, convex cones, fit into the characterization of states in quantum mechanics. The most general kind of state, which is called a mixed state, is given as a convex body or a convex set, convex cone of the pure states. So there are pure states and then there are mixed states, just as there are pure colors and mixed colors. In exactly the same way, you can form the space of these things, and they characterize very specifically probabilities. And in a sense, quantum mechanics is a generalized theory of probability. And what quantum mechanics shows is that probabilities are not just things that we can be ignorant of. Like, for example, if I toss a coin and I put it down on my hand, then you might say, well, it's a 50-50 chance that it's heads or tails, but I just don't know which. And I show you what it is by showing you my hand, showing you the coin on my hand. So you say there, well, it's probability because I just didn't know what it was, but there was a 50-50 chance of it being heads or tails. Okay. What quantum mechanics really says at its heart is that that's not the proper way to understand the probabilities that enter in quantum mechanics. Instead, the proper way is to say, I've got something, and it's not determined whether it is heads or tails until we see it. There was a chance of it being one or the other, and we just didn't know what it was. So the first interpretation of probabilities is called, where it is something one or the other, and I just don't know which. That's called an epistemic interpretation of probabilities, or sometimes a subjective interpretation of a probability. But the case where, in some sense, it's not determined what it is until we do the experiment, and the experiment here is we now see what it is. Before we do that experiment, well, in some sense, it's not determined. It's sometimes called a propensity interpretation of probability. It's a propensity to be one or the other, but until we make the determination, do the experiment, that propensity is merely a possibility. It's merely a propensity to have one outcome over another, and it's not fixed as to what that was by nature. Instead, the experiment determines what it is. That's the difference. An epistemic interpretation of probability, which is how we mostly think of it, and a propensity interpretation where the propensity is a sort of possibility that has to be realized by some kind of experiment. So with that in mind, we now look at quantum mechanics and say something about it. I've introduced this term, pure states and mixed states, deliberately in order to be able to talk about quantum mechanics, because that's the terminology that's used. So let's start where most people get to understand this initially, and that's to be told about the pure states. These are the ones that, as it were, most people get to have an exposure to in a first course in quantum mechanics. So what is a pure state? Well, these get represented in what is called a Hilbert space. And the pure states are the states which are equivalent to the rays of a Hilbert space. So what are the rays of a Hilbert space? Well, the first thing to note is that a Hilbert space is like a vector space, like a Euclidean vector space. Exactly as we had vector spaces in relativity theory, so we also have these vector spaces of, as it were, vectors pointing, in quantum mechanics. One big difference, however, is that in relativity theory, the vector space was what we say is over the real numbers. Whereas in Minkowski's presentation of these vector spaces, the real numbers were the important things, but when we look at quantum mechanics from the outset, we're interested in a vector space over the complex numbers. In other words, our determination of these vectors in this space will be given as sort of, as it were, points in a complex space, a space of complex numbers, which are numbers that which are combinations of real numbers and imaginary numbers. So, for example, 1 plus 5 times the square root of -1 is a complex number. In quantum mechanics, the Hilbert space is like a Euclidean space, except it's a Euclidean space over the complex numbers, and then the idea of distance and length have to be given in terms of the way it is given in the complex numbers. So we get this fundamental difference, and it's, as it were, a huge stumbling block, that in relativity theory, we have a vector space structure over the real numbers, and in quantum mechanics, from the outset, we have a structure which is a vector space over the complex numbers. Now, we don't want all of the vectors in that Hilbert space to represent states. So if two vectors differ by a multiplication by a complex number whose norm is 1, that is, whose length is 1, then we take that as being the same part of the same equivalence class of vectors. And these equivalence classes of vectors are rays in the Hilbert space. So we have these rays in the Hilbert space. They correspond one-to-one with the pure states of a system. There are an infinite number of those complex rays for the Hilbert space. That's the first thing. Now, when we generalize this, we want to think of those as those, even though there are an infinite number of them, as related to or as analogous to the pure colors in the color space. Now we want to think of something as equivalent to the mixed colors. What is going to be equivalent to that? Well, the first thing to do is to note that the rays in a Hilbert space, the infinite set of rays in a Hilbert space, is equivalent to a particular kind of geometry. This was first noted, I think, by von Neumann in 1932, some 7 years after the beginning of quantum mechanics. It was noted by von Neumann. It had been touched on also by Hermann Weyl. I'll come back to this. So the idea that von Neumann noticed is that the pure states, that is, the rays of a Hilbert space. By the way, the Hilbert space can have many dimensions. It can have 1 dimension, 2 dimensions, 3 dimensions, etc., etc., etc. We want to consider the intrinsic structure of these rays of the Hilbert space form, and they form something called a complex projective n space. That is a space of n dimensions, which is complex projective. A complex projective n space. Here is how it's written here. Now, that complex projective space is far more numerous than the primary colors in the color space, because it's infinite in the case of quantum mechanics. It's only finite in the case of the color space. This means that there's a fundamental difference between the color space and the space of states of the pure states of quantum mechanics. How do we get mixtures into this? Well, we mix in the same way that we mix two colors to get, by proportions, to get another color, which is a mix of 50% one, 50% of another color, or 40% of that color and 60% of the other color, or 30 and 70. In the same way, the proportions add up to 1, because we want, as it were, something with, as it were, 100%. So the proportions add up to 1, and we want this to work in quantum mechanics in the same way. So we mix two pure states to get another state which is within that, as it were, the shell or the surface of that convex body, to give us a point within it in the convex hull. So you see now the importance of Minkowski's idea that the pure states determine the points that are within the convex hull of that figure. So the mixed states then have and can have a complex, an awkward structure. But there is one simple case which I can describe quite easily. Let's take the simplest possible case. Suppose we have a single electron, but we could also do this with a photon. They're both, in some ways, they form the same picture in this form. Suppose we look at the pure states of an electron. Now, we're going to only be interested in one aspect of the electron, namely its spin, and that can be either up or down in any direction. Up or down in any direction. And that will form the pure states of that system. So the electron, or photon, is given in its pure states by 2 points that are on the, as it were, the outskirts of this convex body that are in the pure states. So the pure states are 2 points within the complex projective space. In the case of the pure states here, it's a complex projective one-dimensional space, which gives you the surface of a ball, because the complex projective one space gives you something which corresponding in the real numbers to a two-dimensional surface, a two-dimensional sphere. Now, there's a difference here in the way that mathematicians talk about spheres and the way that ordinary folk talk about spheres. Mathematicians think of the sphere as just the surface, as just the shell of this convex shape. And it's called, in this case of the electron and its spin, it's called the Bloch sphere. It's a two-dimensional surface. Now, the inside of that shell is not a sphere, it's called a ball. This is not the way most people use the term sphere. Most people will think, for example, that the Earth is a sphere. Well, strictly it's not. Even if you ignore the bumps on it, it is in fact a ball, because it's got, as it were, a filled inside. A bowling ball comes close to being a ball. It's not a sphere. The outside shape, so the surface of the shape, is a sphere. If it's got, as it were, if you're interested in the sphere surrounding something that's three-dimensional, the Earth, the Sun, bowling ball, etc., cannonball, then it's a ball. If you're interested in that, it's a ball. In this case, it's called the Bloch ball, is the space of mixed states. So if you take 2 points, and they're these, the up and down along a particular direction are antipodal points on that surface. That's Bloch sphere. Now, suppose we were to take a very interesting case of mixing here. Suppose we take a 50-50 mixing of 2 points that are antipodal on the Bloch sphere. Now, the interesting thing is that determines a point that's right in the center of that sphere. 50-50 takes you to the center. Interesting, because if you take those antipodal points and you begin to rotate them around the surface of the sphere, keeping them 50-50, then what you get is the same point in the center of the Bloch ball. And the interesting thing in quantum mechanics is, and this may be the most stunning thing in quantum mechanics for its consequences, is that center, given by the 50-50 ratios all around the ball, all around the shell to the points that are antipodally related to one another, gives you the same point at the center of the ball, which is called, by the way, the singlet state. And it can be, as it were, in one direction, say along an x-axis, as well as on a y-axis, as well as on a z-axis. But as on all of those points, all of the infinity of those points that are antipodally related on the surface of this ball, on the sphere itself, because we're mixing different pure states to give the same mixed state. And it's very like in the case of the color, although it's much more elaborate than in the case of the color, where you mix two different pure colors in many different ways to get the same visible color. But here's the kicker for quantum mechanics. Not only in the colors case, you can't tell the difference. Your visual system can't discern the difference between different ways of making up that mixed state. In the case of quantum mechanics, you cannot discern it by any means. So if you have two different procedures, one you mix two points along, as it were, one particular axis. Someone else makes the same mixed state by using a different axis or a different axis. It is impossible, once you've made that mixed state, it is in principle impossible to tell how that mixed state was made. It is impossible to tell how that mixed state was made. In some sense, once you've got the mixed state, that's as much as you can then know about that state. You can't know how it was made. Even though different experimenters may have made it in different ways, it doesn't matter. You cannot tell. Now, let's go back to what I was saying about mixing in, sort of, as it were, in general. I talked about two different interpretations of probability. One is an interpretation which is the epistemic interpretation, or the subjective probability interpretation. Now, in that case, you may say, well, it is one or the other, but I can't tell which it is yet because you haven't shown me. But it is one or the other. Underneath my hand, it's one or the other. And all I do, I give you information of a pre-existing situation when I say, see what it is now. It is heads or tails. In the case of the single electron, which is given in its states by the block ball, it is impossible to know how it's been made, and so I could do the experiment of finding out, as it were, from its given mixed state, what it was, and that's equivalent to saying, well, it is something. What is it? I'm looking only at a particular axis along which I've got my experimental apparatus aligned. What is it? Well, we know that it's a mixed state, but if you ask, well, what's it a mixed state of? Which axis, as it were, is it a mixed state of? I now show you, and it'll find out, oh, well, it's spin up along this particular axis. Great. Suppose another person, situated as far away as you like, then takes a duplicate electron and does, as it were, the same thing with their duplicate electron. It's also got the same kind of state space, and they do the same kind of experiment along a different axis. They've got the same mixed state. What happens? Well, in that case, they could look at it along a different axis. Their experimental apparatus may be aligned completely differently. They do it off of their axis, and it's spin down. In each case, what you get is a particular outcome as a result of doing the measurement. But the way in which the electron was formed, the way you formed the mixed state, is forgotten. You can't recover it by doing that. You recover a particular value, but you can't recover anything else. And if you could recover how it was made, what you would have is a way of instantaneously getting information from one point in the universe to another, instantaneously, therefore defying the idea in Minkowski space that you can't do that only travel, as it were, only velocities within the light cone are allowed. Instantaneous velocities are not allowed. So if we take that principle, then how the mixed state was made, how it was, in the language of physicists, how it was prepared, cannot be recovered from an experiment on a system. You won't know. Because any way you orient your apparatus will give you one value. It'll be either spin up or spin down. Those are the only two possible things, which is like a heads or tails. You will only be able to get that, but that won't tell you how it was made, what it was, as it were, before you did the reveal. The space of mixed states, in this simple case of a single electron, one single particle, where you're looking at two possible outcomes, the simplest possible case is this Bloch sphere for the pure states, and the internal of that Bloch sphere, which makes the Bloch ball, gives you a simple picture of how the mixed states and the pure states relate to one another. But, and here's the other really interesting thing, how this generalizes when you have three values for a particle, how this translates into that, or how it translates, let's take the case of how it translates into the case of having two electrons. What is going to be the space of pure states for that? Well, we know it's going to be a complex projective space, but what? And what is that complex projective space going to look like as it goes up from 2 dimensions to 3 dimensions to 4 dimensions, etc.? What is it going to look like? It's going to be, for the simplest case of two particles, which are electrons, that space is going to be very, very much larger. The space of pure states and the space of mixed states is much larger, and it's not a space which is easily understood. Where you get to 3 electrons, which you could say, well, 3 electrons is not very much. We're barely scratching the beginning of the periodic table for elements. What do you get with 3 electrons? Well, it becomes hideously complicated. And I don't think that even today it's quite understood what the space of mixed states looks like in that case. Suppose it's a convex shape. How many dimensions does it have? What is the shape of those dimensions? Even with 3 electrons, that's almost nothing. It's unknown what that is going to look like. What we, of course, do know now, it's a fundamental thing, is that within whatever shape these are going to be, what the shape the convex hull is going to be, it's going to have zones of the separability of those two particles, and other cases where the particles are entangled together. So one further puzzle which has to be solved is what is going to be the shape of the entangled particles in whatever shape that is, and that higher dimensional thing is. What is going to be that shape of entangled particles, and how are they going to be related to the subspace of the separable particles? That is, in a sense, where all of this leads. And you can see how essential Minkowski's original idea of convex shapes, convex sets, convex cones, was to all of that process. He's rarely ever mentioned in this, but he is crucial. Now, if you want to follow all of this up, there's one book which I think is supreme to every other in this matter, and it's this book called The Geometry of Quantum Systems, or Geometry of Quantum Systems. It's by two names I can't pronounce. Well, I can pronounce one of them, Ingemar Bengtsson and Carol. I'm not even going to attempt it. I would do a disservice to the author if I were to attempt to pronounce his name. I would surely butcher it. This is one of the best books around. It's available from Amazon. It's a little bit expensive, but nevertheless, it's absolutely worth it. And it's a very modern account. It's huge. It's something like 612 pages. but it gives you everything that you want. I have to say it's a little bit disappointing that it doesn't give you a reference to Minkowski's work on this. Nevertheless, for all that, it's one of the best books you can get. So if you're interested in quantum mechanics, how pure states and how pure states interrelate with the mixed states, how entangled states within that convex shape, how they, as it were, thread in with separable states, then I highly advise you to have a read of this. It's well worth it. It says much more, of course, than my picture. I've tried to simplify it today, but the complexities of all of this, including getting an understanding of what the higher dimensional spaces might look like. Well, this is the only book that I know of that gives you some clue as to all of that. So yes, by all means, I highly recommend it. So that's the second lecture, or second video, if you like, on Minkowski's contribution. It was outstanding and significant, and Minkowski did this some 20-something years, maybe 30 years, before quantum mechanics was even invented. It's normally given, the point at which it was invented was mostly given in 1925, when there was a publication of what is called the three-man paper. The three-man paper, I think it was Bohr, Jordan, and Heisenberg, and it was sort of the official beginning of quantum theory, matrix mechanics, etc., etc. Okay, the person who, by the way, who investigated the color space analogy before anyone else, really, and he wasn't thinking of quantum mechanics when he was doing this, was Schrödinger. But Schrödinger got a handle on this aspect of quantum mechanics quite early on through investigating color spaces. The two people who got onto this very, very quickly, and one for the simple reason that he was the editor of Minkowski's collected papers. He had, as it were, an early insight into everything that Minkowski ever wrote. And his name was Hermann Weyl. Hermann Weyl was the person who was able to make use of Minkowski's ideas because he was the editor of his collected works. And he did so both in terms of relativity theory by investigating what are called affine spaces, because you can turn Minkowski space into an affine space. And he was the first person to investigate how affine spaces can be as it were, the conveyor, or the courier of ideas within relativity theory. But he also had the idea of using Minkowski's idea of convex spaces to describe the pure states and the convex states that they enclose. He did all of that as early as 1927, 2 years after the initiation of quantum mechanics. That is how soon he got onto it. And this was then done also by von Neumann in 1932, based probably partly at least on Weyl's way of describing this. He got onto this and he developed it in terms of related systems which are composed of subsystems, where you have, say, two particles and they're subsystems of a total system. And then from there you have the elaboration of this theme by Schrödinger, who investigated, was one of the first to investigate the whole notion of entanglement. In fact, that term was his. It was a translation of his German term Verschränkung that came from his early work in this area, inspired strongly by von Neumann's book. And this was, as it were, the beginning of everything in quantum mechanics. And he published that work, Schrödinger published that work in 1935, as did Einstein, his seminal paper on the Einstein-Podolsky-Rosen paradox. From 1935, you may say, what happened? Well, the whole notion of entanglement was mostly forgotten for 50 years, from 1935 to somewhere in the 80s. Early 90s. I mean, I remember people in the early 2000s being physicists, not having heard at all of entanglement. Not at all. And yet, in their own area of physics, this was something that was just unknown. Schrödinger's work was just forgotten. The only thing that got remembered, which was remembered eventually, was this idea of Schrödinger's cat. Schrödinger's cat is insignificant in comparison with his other points that he made in those papers in 1935. He discovered, he was the one who named and understood the fundamental character of entanglement. He didn't follow it up. He didn't remind people of what this was. And no one else read this stuff. Or they didn't care about it, or they didn't understand it, or they were doubtful about its cogency, or whatever it was. That was the outcome. So for 50 years, quantum mechanics was kind of dead, buried. And it wasn't revived until people in the 1980s, 90s began to think about it. Particularly the one who initiated the thinking about it was John Bell, the Northern Ireland physicist. That woke everything up suddenly. And that was early 60s. But that's still 30 years after Schrödinger's paper. And Bell himself may not initially have known about Schrödinger's papers. We have been very delayed in understanding all of this, and that those delays are shameful, really, shameful, in the way that this was done and then missed. Just not spoken about. And I think partly the blame, if one wants to be reasonable in making this accusation, then much of the blame has to be put on the Second World War. It made physicists concentrate on very practical ways of understanding quantum mechanics and how it was to be employed in, for example, making the atomic bomb. That led people into a practical, applied physics idea in which the mathematics shifted, as it were, infinitely far into the background. And for the much of from 1935 onwards, the high mathematics, which had been brought into quantum mechanics by Hermann Weyl, by Eugene Wigner, by John von Neumann, all of that was forgotten or lost or not in the consciousness of those who were supposed to be most engaged in it. So that is one of the casualties of the Second World War. Perhaps not the most important, but certainly an important casualty. If you're driven to looking at the physics as something to do with how you make things, how you understand the workings of nature in a very practical way, then you may well not understand the mathematical richness that is sitting behind that theory. And it was that mathematical richness that was for so long forgotten. But that is not the case anymore. From now, it is the case that everyone is aware of the importance of this idea of entanglement, and they're coming aware, thanks to this book, of the mathematical richness of the spatial aspects of these states. So to understand beyond two particles, to understand how entanglement works is it's going to be a real challenge, the challenge of the next 100 years at least. And we're at the very, very edge of that sea, barely getting our toes wet. Two particles is nothing compared to the number of particles in the universe. When you start to think about the size of those state spaces, well, if one doesn't say the word boggling at this point, then one has not really said enough. I'll leave you with that. See you in the next lecture, talk, video, whatever you like. Please like, subscribe, blah, blah, blah.